Just to start out, I wanted to give a little bit of an intro here as to what Advent of Code is, if you're not familiar with it, and step through a little bit of what it looks like to solve a problem. So it is an Advent calendar style set of code challenges, so runs every day through December. Each day at midnight, you get a new problem. Each problem is actually two parts, and I'll talk a little bit about that later. And it's a variety of different styles of problems, and that's actually one of the things I really find very fun, in that it's a little bit different from some of the leak code style challenges that are strictly more focused on algorithmic problems and sort of interview practice. There's a bigger variety, and a lot of the problems lend themselves to different types of solutions. I've seen people come up with pencil and paper or Excel-based solutions even to things, which is kind of a fun way of thinking about it, and a little bit different from sort of your standard interview prep type problems. There's also a competitive aspect to it. You don't have to compete, but there is a leaderboard. It is very competitive for people who compete on the global leaderboard, and it's almost amazing sometimes to look at it. There are people who sometimes will have solutions within seconds of the problems being released. But you also have the opportunity to set up private leaderboards too, which is a great way. If you want to compete or even just sort of compare solutions among friends, you can set up a private leaderboard and invite people. And Puppy does have a leaderboard. If anyone wants to participate, it's in the banner on our Slack channel, and welcome to join and take part with us if you'd like. It's also a great way to see code in a bunch of different languages, styles, approaches. A lot of people use this as an opportunity to explore a new language, a new platform, a new style of writing code, a new tool. And a lot of people share their solutions. So it can be a great way to just go out and get a chance to read some code and see how other people are doing things, especially if you're working along with it. Even if you don't solve the problem, if you've read about it and thought about it and then go look at sort of the variety of solutions people come up with, it can be pretty amazing, and it's a great way to learn new approaches, new languages, new styles. And I just think it's a lot of fun. I have done it at least part of the month, almost every year it's run for, I think we're in the 10th year now. So I hope if you haven't tried it, this will inspire you to take a look. And if you do participate, maybe you'll learn something today that you can take away to help you with your solutions. So I'm going to run real quick through a day one problem. Historically, the day one problems are fairly short, fairly approachable, and have a solution that's pretty straightforward, which lends itself well to a quick presentation here. And it's also an older one, so I'm not going to spoil it if you're participating this year. So one aspect of these problems is that they tend to come with a bit of story, and there's a little bit of work to sort of extract what do I need to do from the narrative of the story. And there is sort of an ongoing story through the month each year, too. And as part of this, I've sort of broken this out a little bit as what you will see this in the problem itself would be all presented as one page. But once you sort of dig out what is the thing I need to do, you'll come up with a set of instructions. And they tend to be fairly prescriptive, but maybe not 100% detailed as to all of the scenarios you may need to deal with. So it gives you enough to start thinking about what a solution looks like, but they're usually not enough to completely derive a correct solution. You're also always given a set of examples, and they tend to be short, small examples that are a scale that you could actually walk through by hand, even if the problem itself is bigger than you could solve by hand. And I also love to use these as my initial test cases. They're usually not sufficient to test everything you might want to test, but if you aren't passing these, you're not going to pass the full input either. So I always...
This is not true and terrifying.
Sorry? Oh yeah, these are absolutely not sufficient to pass the final. Yes, yes. If you pass all these and then don't pass the full input, that's always a fun challenge. And then finally you get your full input, which is going to be the same format as your test cases, but is much longer. typically, or at least leads to much more computation typically. Sometimes the inputs themselves may be pretty small, but can blow up in terms of how much compute is required. So I'm just going to step through real quick. The problem basically says we're starting at a start point, and we're going to turn and step according to the sequence of instructions we're given. So we turn right and take 5 steps. We turn left and take 5 steps, right and 5, right and 3. And our solution we know is 12 blocks away, and we can confirm that indeed, sort of by city block orthogonal distances there, we are in fact 12 blocks away. So thinking through just a simple solution, very direct solution to this, if we track our current position as an xy tuple, track our current direction as an xy vector, that is the direction we're going to take steps, and then just iterate through tracking our changing position and direction as we receive the turns and steps each time, and then take the sum of the horizontal and vertical differences at our final position. That should give us our answer. So just a very quick, direct implementation of this. We define a few constants. We're going to use the input strings as keys in a dict to make it simple to parse our input. We have a north direction constant and our step vectors that are the various directions we can step. We define a real quick little helper to add a pair in a tuple so that we don't have to do more. If I were not writing this on a slide, you might want to do this as a class or a named tuple or something a bit more formal, but this is compact. And then we also have to do some parsing. So we open up a file, read it, and then parse it. So we're going to get a sequence of tuples where we have a left or right turn as a string and a number of steps as our final parsed input. And then our implementation is pretty direct. We start out at 0, 0, facing north, and then each time we take a turn and a number of steps. We change our direction based on that turn, and then we add our step vector to our position each step, and print out at the very end the absolute value of the final x and y. And it in fact works. One thing the organizers do ask is that you not share your actual answer or your full input. Everyone gets a somewhat random set of input values for their problems, but there is a finite number of them, so they do ask that you not share your full input or the final answer, so to help minimize the amount of abuse. So I'm not going to put it here for posterity, but I'll trust that as long as I didn't mess anything up transferring it onto the slide, this does in fact work. But then that leads us to, when you get a correct answer to part 1, and only when you get a correct answer to part 1, you get access to the challenge for part 2. And that's actually another really fun thing I find in these problems, that part 2 is always some sort of a twist. It's some sort of an extension or change or modification or addition to the part 1 challenge. And it can be really fun to try and design your part 1 to make it as easy and as fast as possible to solve part 2. If you do it well, sometimes part 2 may just be changing a constant or changing a function call or adding a line or 2 of code. So here the twist is that we don't actually care about our final position. We care where is the first location that we visit twice. So in this example, we sort of do a little loop going around 4 right turns and cross over our previous path. So based on how we did it before, we can actually modify this and come up with a very simple solution that's only a few lines of change from our previous. If we simply keep a set, remembering where we visited, and each time we check as we take a step if we've been to this point before, and if so, we found our first. Otherwise, we remember that we have visited it and continue on as before. So I chose this one specifically because it's kind of a good example of some patterns and common practices that I think are useful across Advent of Code in general. The text manipulation is something that if you're going to do these problems, you need to get used to a little bit. Almost everything is going to have some sort of text processing to get your input into a format that you can work with. Here I did a little bit of strip, split, int casting. That works for a lot of things, but sometimes you'll want to do more. Regular expressions can be super helpful here. Sometimes it's worth stepping up to using some sort of a full parser. Grids and coordinates are also something that come up repeatedly. So get used to it, maybe even build up a library that works for you to track coordinates. I also find it super helpful to not throw away intermediate results in my part one. If I can either save them if it's not too compute and memory heavy, or at least make it easy to save, it often makes the part two implementation way easier to have access to that when you find out what the modification is there. Sets and dictionaries solve a lot of problems for you. And it's helpful to have a little bit and maybe more than a little bit of math. So I think that's a good sort of overview of what a question is like, and that's pretty representative of what solutions to them are going to look like. And then Matt is going to come up and talk about the less than a little bit of math.
Yeah, I'm pretty sure it's set me up with that one. Okay, if you've seen me talk before, I always talk about math because I love math. Oh yeah, I definitely can. Am I too quiet? Okay, I have teacher voice, but maybe not tonight. Okay, so I always talk about math, so I'm going to talk about math. I'm going to talk about common geometric phenomena that comes up in these problems. So they'll often give you a grid, and they'll ask you something about some geometric property of the grid. So in this case, we have a grid of squares. It is given to you as this list of coordinates. So that coordinate 3, 2 is the one down in the left, and then we're going around and zigging around. So the coordinate 10, 2 is the one all the way on the right at the bottom, and then as you run through the list, we go through the black dots that are at the corner of this like geometric polygon looking thing that I made. First part of the challenge, this is a common thing that happens in these questions, is to ask you for the perimeter of the shape. So here I added a green line around the perimeter. It's not a line, it's like many line segments put together, but allow me calling it a line. And the perimeter is how many boxes does the green line go through. This is somewhat straightforward, but if you're a new programmer, it might be kind of challenging as maybe some ambition. Here is a very efficient way to compute the perimeter of that. It doesn't work if any of the lines are diagonal, and it is an exercise for the listener to fix it so that it works if any of the lines are diagonal. So I'm going to skip the perimeter part. If you use it here, you get 36, and that's correct. Did anybody count? So you're all trusted me. So the interesting part of this problem, to me, the mathematician, is the second part, which asks, what's the area? The total number of green squares. If you have like a small number, like I do here, you can solve it on pencil and paper by just like literally counting. But usually the input for these problems are on the order of that list of coordinates being hundreds or thousands. So the answer to the problem can be on the order of millions or trillions. And you can't print out the shape, and you can't just count them. So how do I compute the area of this shape from just the list of coordinates? So a really useful formula that you may have learned in geometry, but probably didn't, is called the trapezoidal formula. This goes back to Newton. And it gives the area of a polygon by summing up a bunch of trapezoids. So I'm going to wait like 10 seconds and imagine some trapezoids, and then I'll show you the trapezoids. Those are the trapezoids. So each edge, if it goes to the right, from the left to the right, you get a green trapezoid. And if it's going from the right to the left, I made a purple one. And to get the area of the polygon, you add up all the green trapezoidal areas, and you subtract off the areas of the purple polygons. And you can see, like, we've added the bottom that's below the polygon, and then we've killed it by subtracting it when we go backwards for the purple ones. As a fun fact, if you take this idea way, way too far and you do calculus and you make the polygons become like infinitely small, you get a formula called Green's formula, which is probably on page like 400 of your calculus textbook. Maybe you don't know how to calculate the area of a trapezoid. It's actually a rectangle where you cut out a triangle and put it in a different place. So a trapezoid is a rectangle where you cut off a corner and put it on the other corner. So the area of a trapezoid is actually just the area of a rectangle for like an appropriate rectangle where you took half of the heights. So we're going to do that. We're going to try that out on our shape, and I'm going to use this trapezoid formula. I'm going to write it as a function. You can see the average is up there with the divide by 2. There's a plus, and then there's a minus, which is the width of the trapezoid. And we're going to go for it, and we get 41, and that's too small. So exercise for the reader. Why did we get too small of an answer? I'm just going to count to 5. We got too small because I didn't include the area like outside the lines that are part of the boxes but not inside the lines. So now we have 2 opportunities. We can try to like be accountants and like account for all of those small areas, or we can be absolute Wikipedia masters and find this Wikipedia page for Pick's formula. Pick's formula is something that like is not commonly taught. It's a trick that you learn by doing these problems enough and hanging out on Reddit. What it does is it counts the number of dots enclosed by the perimeter, like strictly inside of the perimeter. And it says if you know the area inside of a shape and you know the perimeter of the shape, I can tell you how many dots are inside it. The technical term for those dots is lattice points. So lucky for us, we just calculated the area, and in the first part of the problem, they set me up, and I already calculated the perimeter. So I have both of the ingredients to calculate how many little dots are inside. Pick's formula is remarkably simple, and it looks like a lie. It's that. You take the area, you add 1, and you subtract the perimeter divided by 2. The fact that this gives you the number of dots inside of the shape is one of those like God-given mathematical facts that we don't deserve, but like, thanks. You get 24, and if you count, there's 24 dots. So, sweet. And now we got the whole thing, because we know the perimeter, we know how many dots are on the line, we know how many dots are within the line, and if we just like add them together, we get 60, and did anybody count? This one I counted, it is 60. That's how you do this. So that's Pick's formula, that's the trapezoidal formula. Yeah, thanks. I like geometry, it's cool. So next up is my man Tevon. He's going to talk about static typing.
All right, everyone. So my name's Tevon. I work with Matt over at Remitly, and today I'm going to talk about why, what I think are the advantages of using dynamic programming languages like Python for solving advent of code. I self-describe myself as a static typing enthusiast who just keeps coming back to Python. And to understand why, we're going to dig into this question a little bit. So the Python community has been spending the better part of the last decade adding type hints to the language, and the community has put a ton of support into covering the entire standard library with static type hints. But when we look at the standard library's documentation, we still see documentation like this. And you can see here that we reference number and string as the parameters for these floats, but these aren't static type hints. These are just descriptions of what kinds of inputs this function takes. The reason why the standard library doesn't show the static type hints is because of features like this. So this is the LRU cache function, which is a function or decorator as part of the functools package in the standard library. If you're not familiar with this, it's essentially a way to mark your function as being cached. So if you call that function twice with the same parameters, the first time the function will actually run and compute the result, and then it'll cache the value so that the second time it's called, it just returns that cached value and saves out on some work. This is mostly useful if you have a relatively expensive function that you plan on calling a whole bunch of times. So why does this matter for advent of code? So we're going to step back in time to advent of code 2020. This is problem 10 or day 10, part 2. And essentially this problem boils down to, we're given a list of sorted integer values that has a fixed starting and ending point, and we want to count all of the different ways we can pick values from between those two endpoints such that the list is always increasing and the gap between subsequent values is never more than 3. So one way to think about this problem is this graph on the right-hand side here. So this is showing all of the possible ways that we can pick numbers from this list so that they're always increasing. The dotted lines are invalid paths. There's a jump more than 3, so you can see like going straight from 0 at the top to 11 at the bottom, that's way too big of a jump, not a valid path. But if we trace along all of these thick black lines, those are all of the valid steps. And so we're trying to count all of the distinct paths following through these thick black lines. So how hard can this be? Well, my answer here was around 32 trillion valid paths. So to put that into perspective, if we took a millisecond to check each of those paths, it would take over 1,000 years to complete. So what do? My solution here was based on the observation that I made about, if we just kind of jump to the end of this problem, we focus on node 8, so it's like the second node from the bottom there. No matter how we get to node 8, there's always only 2 more paths to get to the end, right? We can go from 8 to 11 directly, or we can go from 8 to 10 to 11. So this is a really important observation for 2 reasons. One, it suggests a kind of recursive solution. If we start from the end and work our way backwards, we can count the number of paths from that point to the end, and then just keep kind of multiplying as we go up to aggregate the total number of paths to get from start to end. And the second is that there's this notion of duplicate work, right? No matter how we get to 8, we're going to count 2 paths from that point on. And that means that if we have 10 ways to get to node 8, we're going to keep counting the last 2 paths over and over. So this leads us back to this LRU cache, right? We have recursion, so we're calling the same function over and over again. And we have duplicate work because once we get to node 8, we're going to count those last 2 paths over and over again. So what does this have to do with the idea of static typing and dynamic typing? Well, this is the actual type stub for the LRU cache function. It's a lot messier than those docs suggest. The important thing to note here is that at the very bottom, that final overload is really what we're looking for. Essentially, LRU cache takes a callable function as input, and it's going to produce this LRU cache wrapper, which is really just a wrapper around another function as the output. But if you look closely, there's something strange going on here. There's these dots. Oh, was it not? Yeah. So there's these dots in the type parameters for this callable function. If you don't know what those are, don't feel bad because a lot of people don't. There's a whole page in the Python standard library documentation about the meaning of ... specifically in the context of callable as a type. And what it says is that this is a gradual form. If you don't know what that is, you can click the link and it leads us to this. So a gradual form is an element of a type expression which makes that type, the type that it's part of, not a fully static type, but rather a representation of a set of possible static types. Basically, it means that we're bailing out the static type system that we put all of this effort into providing these type hints for because it's not feasible for this static type checker to reason about it for whatever reason. And lest you think that this is a problem just for Python, something fun that I did for AOC 2020 is that I did each problem in 3 languages. I did them in Python first, and I translated it to Rust and OCaml just as a way to learn those 2 new languages. And what I found is that translating my solution from Python into these languages was a gigantic pain because trying to define this type of functionality, like an LRU cache, in those languages is challenging. So I was able to find a way to do it in Rust. There's this nice crate called hash that uses something called proc macros to generate special forms of that memoization function or that LRU cache function for every function that it decorates. This is kind of cheating because proc macros work by transforming actual language code under the covers. They use sort of a different set of static typing rules. And so you're generating a valid statically typed function at the end of it, but it's doing that by modifying source code. So it's a little bit weird. For other languages like Java that don't have metaprogramming tools or don't focus on those as a means of implementing features in the language, they typically either resort to just supporting caching for functions with specific numbers of arguments. In the case of Java, they'll let you cache functions with exactly 1 argument, that's it. Or they'll use runtime reflection to work around the limitations of the type checker. So as anyone that's used either of these features, you can imagine, it's not really a lot of fun to have to refactor your code to fit having only 1 argument. I've already gone through this work in part 1 my problem and I have this 3-parameter function. If I want to use caching, I don't want to go back and refactor that. And runtime type reflection has all of the problems of dynamic programming, right? Like you lose your static typing. So neither of those really feel like satisfying solutions. So what gives? Why is this so hard? What we really want is the ability to define a function like this. Memoize takes a function as its input, and it returns a function as its output, and the parameters in the return value of that input function match the output function. So this is what we want to do, but if we try to put this into Pywrite or MyPy or any of the other static typing tools for Python, you'll get an error like this. It says expected parameter type list or ... There's our ... again. The problem is that callable takes a list of type parameters as its first value, not just a single type parameter. And so the static type system is designed to reason about types at the individual type level and doesn't have any way to enforce constraints or reason about constraints across lists of types. So what's the takeaway from all of this? So here's my actual solution to that problem. I wrote this valid combinations function. It's a recursive function to satisfy going through and checking all of the different paths in that tree that I showed earlier. And I ran this, it worked on the example just fine, completed in a couple of milliseconds. And then I ran it with my actual input and I stared at it for a while and kept spinning and then didn't finish. And eventually, I killed the terminal and I came back, I imported functools, I added the LRE cache function, and now this runs in about 150 milliseconds. The takeaway here is not that static typing isn't good or not helpful. You can see here, I even added type hints to my code here. It's that if you go into the process of problem solving with the goal of satisfying your type checker, there's a risk that you're sort of tossing aside or ignoring an entire universe of solutions that are valid, sound solutions. They're even type-safe solutions, just not something that your type checker can reason about and validate. And that's all I got.
Thanks, Devin. Okay, Drew. So you muted it? Okay. So we're swapping computers, right?
Yep. And I'm going to need the hands-free microphone so I can operate a computer while I'm speaking.
I think that's this one. So I think you just lapel it and then push the button. Okay, to wrap us up, we have Janet. She's going to talk about testing in the context of admin and code problems.
So can people hear me okay? What do I need to do
I think
here?
you need it higher, the
Higher.
microphone. Yeah. There you go.
Is that better?
It's directional.
Wait a minute. So,
They're annoying.
is that better?
Okay, I'll just hold
Is that better?
Yeah.
Okay.
Yeah, okay.
Got to push the buttons here. Okay. So yeah, my theme is advent of code time savers because, it comes out at 9 o'clock and you want to go to bed at a decent hour, right? So the first library that's kind of handy for advent of code is called parse. And so it's for when your input is a little too much to just fix with stir.split, but it's not really worth writing a whole regular expression for. So if you have an example input text of button A : x plus 26, y plus 66, you can just take that and turn it into like a format statement backwards. And so I import parse as p, and I say I'm going to expect something that looks like this, and they can pull out two ints. Basically, those :ds are just format strings, and they'll go into ax and ay. Another cool one is called ice cream. Better debugging print statements. What I really like about ice cream is that you can turn it on and off easily. So you're checking your input and you make sure you parsed it right and you got the right number of numbers and they look kind of like your input file or whatever. You can say like I see input nums and see that it works. And then after you've done that with your little sample example, you can disable it so you don't, when you get to that one with 1,000 numbers, you're not printing all that out on your screen. PyTest is another really cool one. I didn't realize this until I was trying to write a nice starter file for advent of code, but you can call it as a function and never leave your solution.py file, just call pytest.main. And so I will run pytest.main. This -- capture t sys is so that my ice cream output shows up on my terminal and PyTest doesn't snatch it from me. And dash V is just this verbose output if you want it. So you test it against your sample, and then if it works, great, you go on to your full one. If it doesn't work, you can make your main stop right there. And finally, an automated code runner of some sort. So you write stuff, you print some stuff out. You're kind of going back and forth between writing your code and running it, and writing your code and running it. It's really nice to just have a little function that's watching, and every time you save it, it executes your code, and you can just kind of stay in an immediate feedback loop. So on to that dangerous thing, the demo. This is my watcher function. I used the same, no, I don't need to scroll my network here. So I used the same problem that Andrew started out with. So I wrote a solution to 2016 day one. Here's my thing to take each L and R number, and I used parse to parse it so that I could do a demo of it. And I'm looking for one letter and one number on each piece of string. And then I'm saving it in a little name tuple, what way to turn, how many blocks to go. I didn't use north, south, east, west and numbers. They're all arrows pointing up, down, left, and right. But the same general idea of what he was showing. I didn't get a chance to see his code before I wrote mine. I take my cursor, it's at some location, facing some direction, it gets some instructions. If I'm turning left, I get the new direction from the left turns dictionary, otherwise I get it from the right turns dictionary. Calculate my new location and return a new cursor. And my solve says, okay, I'm gonna parse through all of my instructions, get my first cursor, walk through the steps. But my test failed. So normally what you would be doing, like I said, is writing a little bit of code, seeing your prints fail, your tests fail, and then going back and forth. I wrote all the code up front to make the demo go faster. But I can see that I couldn't unpack a none type object. My parse failed. And I can look at the input to that was space L3. Oh, I forgot there was a space, not just a comma. Sorry about that. So I can put this in here. And as soon as I save it, I've got a new problem. My parser now works. It should have worked. Cannot parse. Did I save it? Ugh. I gotta use enough fingers here. Maybe this isn't gonna be good. Why did I do a live demo? So let's see here. Cannot unpack. Did I put through, comma, space. So I didn't actually fix the bug correctly. Comma, space. Okay, so now if I use, there we go. So now I've got it actually running the code, and I was supposed to get the answer 5, but I'm getting the answer 2. And so I'm going to throw in some print statements here. Let's look at the cursor with IC. And here, let's look at what step I did and the cursor that came back. And save it. And like normally you'd have like a wide screen and you can see these two things side by side. And you say, oh, okay, so I started at 0. I went R2. Wait a second. I went from 0, 0 to 1, 1. I'm only supposed to be stepping either up or down, not both. So let's go take a look. What happened there? Oh, there's some copy paste errors here. That should have been a 0. And I'm going to just go ahead and fix the second bug too in the interest of time, since I think we're supposed to be finishing up. But there's another bug here where I just step one step regardless of how many are in the instructions. So the instructions are telling me how many blocks to go, and I did not multiply that. So I'm going to put that in there as well. And we'll save that. And why didn't this rerun? Did I? So I got one more bug still that I haven't fixed. So it ran, doing better, but it says assert -1 equals 5, and that's because I didn't do the absolute value at the end there. So I'm going to have to sum int I for I incur. And that's supposed to be absolute. So if we take the absolute values, now on my test pass, and I can go on to my real output. But it's really nice. It was only like 10 lines of code to write this, and if you have those two things running side by side without having to flip back and forth like I'm doing in this demo, it's a really smooth way to get into a rapid feedback loop and finish your advent of code stuff easily.